All right, quick review from last class. Happy Fun Math Day, because the sun is out today in Pendleton, Oregon. We want to estimate the error using partial sums for the first 50 terms. So before we do the error, it's a good idea just to see what is S sub 50. So we should plug that into some kind of, whoa, it moved on me. Darn. All right. Okay, we'll switch to this other thingy here. Then I can, then I got to stand out of your way somehow. All right, so can I grab you and throw you away? Yes, look at that. Gotta love technology. And then I need a pen again. Okay, so let's find S sub 50. So we'll need some technology for that. So if you happen to have some portable technology that can add up sums, whip it out. Otherwise, I will do it up here too. So I want to know what is the sum as k goes from 1 to 50 for 10 over k to the 7th. So I'm going to have to ask Desmos about that. Wolfram alpha is another good source for adding stuff up. All right, so let's see. We want the first 50. So let's adjust my sum adder. And we want, let's see, there was a 10 in the numerator, and there's an I here to the 7th. Okay, so there's that sum. It's looking pretty darn flat up there, isn't it? All right, so then I just need to zoom a little. X, if you would please go out to, say, 55. And Y could go, oops, from 0 to, oh, I guess we could go from, that's hanging right around 10, huh? So maybe from 9 to 11. All right. And so out to 3 decimal places, I get it's about 10.083. Is that what your computers tell you? That's what you got? Did you get that? Was it 10 over? Did I get the wrong one? Yeah, 10 over k to the 7th. Yeah, I think I got the right one there. Okay, so we're at about 10.083. So we want to know how close is that to the actual one? And I'm not sure how to tell Desmos to give me more decimal places. How many do you have there? All right, give me 5 of them. 10.08349. Okay, so let's see how accurate that is approximately. And so we have a theorem we went over the other day in class that says the error, which is all the terms after 50. So just a reminder, the 50th error sum would be 10 over 51 to the 7th plus 10 over 52 to the 7th, and so on down the line. So again, that's the same kind of sum as k goes from 51 to infinity of our 10 over k to the 7ths. And so our theorem says that the error is going to be bound between, on one side, the integral from n plus 1 to infinity of whatever we decide f of x is. And on the other side, the integral, let's see, I think I wrote these backwards. This one is the n plus 1. It's smaller because we start later. Now, let's fix that. Is that my eraser? Yep. Let's see, pen back of our f of x dx. So we just need to calculate, well, what is integral of f of x from some a to some b? So let's do that next so we can get bounds on that. So we want to know what is the integral from a to b of 10 over x to the 7th dx. So let's see, antiderivative for x to the negative 7th would be x to the negative 6th, and then multiply by negative 1/6. So we're going to have a 10 over negative 6 here, and we're going to have a 1 over x to the 6th, if I write it that way, evaluated from a to b. Now A is either going to be the n or the n plus 1. We'll worry about that after. The B is going to be going out to infinity. So that's the next stage here. We want to say, okay, what's the limit as B goes to infinity? And this is one of the P series we talked about the other day. We know ahead of time it's convergent. That's why we're even bothering here. If this wasn't an easily recognizable series, then I would have to do some more work first, like apply the integral test in the first place. So I kind of skipped all that stuff. My apologies. I'll review the basics in just a sec. So let's see, what do we have here? When we plug in the B, we're going to get, that reduces a little. What does that become? 5/3. So negative 5/3, 1 over B to the 6th. And then we'll have a minus a negative, so a plus 5/3, 1 over A to the 6th. And pretty straightforward here, as B gets large, the fraction here goes to 0, so this thing just disappears. And so what we find here is that when we do apply the limit to our improper integral, we're going to end up with a 5/3 times 1 over A to the 6th as what we evaluate. So now we can put boundaries on our 50th error. So for us, n is 50, so that means we need to look at 50 on one side and 51 on the other. So new page, gotcha. So our 50th error on the left, or right and left, excuse me. I think I need to move over here so it looks better. There we go. So let's see, on this side we have our n, right? So we're going to have 5/3 times 1 over 50 to the 7th. And the other side, we're going to have 5/3 times 1 over 51 to the 7th. So this just says the actual error is going to be somewhere in between these two numbers, how far we're off. The computer program only asked us for an upper bound on the error, so they only wanted this side here. So we need to whip out a calculator, see what we get for possible errors there. So, oops, come on, there you are. I'm just going to go to my Google calculator. What is 5/3 divided by 50 raised to the 6th, right? And my calculator says it is, ooh, wow. We're getting pretty accurate there. So we got 9 decimal places of zeros. Is that what you're getting to? About 1 times 10 to the negative 10th. So that's the worst our error is. The lowest our error is if I plug a 51 in there, and that one says I have 10 decimal places of accuracy. So we have 9 or 10 decimal places of accuracy in this answer here. We're somewhere in between. And so let's see, how does the homework system react to that? I'm trying to remember what I plugged in for. I think 0 is going to be sufficient here, I bet, which isn't really true. Ooh, it didn't like that. Okay. So 0.123456789 Get that right? What I had in the first calculation? What? Uh-oh. Did I make a mistake somewhere? I don't think so. Let's see. Put the 50 back in there. Tenth place should be a 1. And the computer says no, which either means I'm wrong right now or the way I programmed it to do this problem is incorrect. Oh, it's got a show answer right there. Ha, good eyes. Oh, it wanted the scientific notation. Really? I don't remember programming that in. Okay, fine. Let's see what happens if I type that in. 1 point, let's go 0.7 times 10 raised to the negative tenths. Okay, and then submits. Doesn't like that one either. Huh, okay. So apparently this was a badly designed problem by me. And I will, if you get marked wrong, let me know and I will review it. So let me make a note to check that out later. Oh wait, I bet it's looking at this separate. So what if I go 667? It says that one's okay. All right, I got to rethink how that one accepts answers. This is 410.4, number E10. Answer boundaries. Okay. So we had approximated this series out to, oops, wrong way, 5 decimal places, and according to the calculation we did, each of these is actually a correct decimal for the actual answer, whatever that number happens to be. Now we can't name it in particular, like is this some version of pi or e or some crazy square root or cube root or 7th root or whatever, but we know we can identify as many places of accuracy as somebody desires. Okay, and in this case, what do we got? Let's see, back here. On this side, that would be what, 0.1, 2, 3, 4, 5, 6, 7, 8, 9, and then the 1 is there. Tenths, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, billions. So we've got this out to the nearest billionth with 50 terms added up. That's usually pretty good for most scenarios, even if you're building a very complicated bridge. I think we would be all right. Some series very slowly converge, some converge very fast. So we're going to take a look at some other kinds of series that don't quite fit our rules so well and look at comparison tests. So we have 2 kinds of comparisons that we can apply. Ooh, what happened to my pen? There you go. One kind, let's call that A, those are direct comparisons. And then B, the other kind of comparison we'll do is what's called a limit comparison. And so the tools that we have to work with are growing for analyzing series. So we're going to add a couple of these 2 tools today. So direct comparison, let's look at that one first. So let's suppose we have 2 sequences, sequence A and sequence B. And we'll play 2 different scenarios. And each of these scenarios is going to be based on this inequality right here. So every single one of the A's is always smaller than the corresponding B at that stage, at whatever point we look. So one possibility is that if the sum of the A's, if these guys diverge, okay, so when I start adding them up, they keep getting bigger and bigger and bigger in the sum. Well, if all the B's are bigger, its sum must diverge too. You with me, right? Squeezing it away from 0 or some limit. So if we have this to be true and the inequality above, then the sum of the B's must also diverge. So that's one possibility. Another possibility. If instead, let's say the B's, the bigger ones, let's suppose those guys converge. So this is very directional. If the B's converge and the A's are always smaller, well, they're squeezing them can converge too. Right? So then we're going to have the sum of the A's has to converge also. So it's just an application of the squeeze idea. So we'll look at a couple of examples of this. All right, so example number 1. Consider the sum of 1 over k minus 1. As k goes from, let's say, 2 to infinity. And I want to know, what does this do? Is this converging or diverging? Now, what's the first thing we apply to any series when we see it? The divergence test, right? So we say, okay, forget about the sum for a minute. What are the 1 over k minus 1s doing? Well, they're going to 0, which means, darn, I don't know anything. But we always should start that in our head and write it down if it seems complicated. This one's pretty straightforward. So this divergence test tells us nothing here. Can we say it fails the divergence test? I guess we don't know anything. The only way to pass the divergence test is to diverge, right? To have a non-zero limit of terms. So then I'm thinking, well, wait a minute. Let's see. What does that look like? If k is 2, that's 1 over 1. And if k is 3, that's 1 over 2. Oops. Come on, pen. Stop it. 2. This is starting to look familiar. What is this sequence right here? Harmonic. Harmonic sequence we proved with an integral. Actually, we proved it 2 ways. We proved it by just doing a squeeze on it and doing an integral. This is the harmonic series, and we know it diverges. So I could be done, but I just want to apply that direct convergence, direct comparison. So I just want to compare this with a series I know. Well, the series I'm thinking about that's known is the sum of the 1 over k's. So I know that's the harmonic series. The harmonic series diverges. And so what is the relationship between the 1 over k's and the 1 over k minus 1s? Well, let's see. We made the denominator smaller here, which means the fraction bigger. So we get this direction right there. Okay, and so that's my inequality about the terms, the AK, BK. Now I know, oops, also that this as a sum diverges. And at any stage, these guys over here are the same or a little bit bigger. And so they are above these guys over here. So that forces them to diverge also. Okay, so that's just what we call direct comparison. It's just an inequality. So that right there implies that the sum of the 1 over k minus 1s diverge also. And I mentioned the other day that the first couple of things I do when I get any series is, one, I say, all right, what's the limit? Forget about the sum. What's the limit of the terms? Can I just say, hey, you guys don't have a chance because you're not going to 0? If that doesn't give me anything, then I actually list out the terms and I say, okay, do you look familiar when I write you out like that? Because a lot of this is about familiarity. Is this something I've seen before? Can that help me prove it? So really, I didn't even need to go to the comparison test. I was kind of done right there. Okay, but sometimes I need the comparison test for more complicated ones. Let's look at another one. Suppose instead I look at the sum of 1 over 2k minus 1 as k goes from 1 to infinity. What are these guys doing? So I'm thinking the divergence test, as k gets big, the denominator gets big, but the numerator's frozen at 1. So that means each term goes to 0. As we move out, that doesn't help anything. So moving on from there, I list out some terms. So if k is 1, I get 1. If k is 2, I get 1/3. If k is 3, I get 1/5. Oh, okay. It looks like this is the sum of the reciprocals of the odd numbers. Now, this is kind of sort of related to the harmonic series. You with me? Okay. Harmonic series would be, let's see, I really need a different color. Where are my colors? Oh no. Share the screen. All right. We'll record this later with you, but not the internet. Yeah, so let's see, what do I want to do from here? I'm just going to share it now and fix it later. Okay, so we're looking at the comparison theorem, and we're going to do the direct comparison first. So here is our theorem for direct comparisons, and we are going to see how that applies to this right here. So I'm thinking, well, this reminds me of the sum as k goes from 1 to infinity of 1 over k. And so I line them up. Well, that's 1 and 1/2 and 1/5 and 1/7. No, I'm sorry. That one above distracted me. Okay, 1/3 and 1/4 and so on. So how do these compare? Well, at first we're the same, but then once I move on to the second term here, I have that the black series is smaller. Okay, so I have 1 over 2k minus 1 is less than or equal to, by observation, 1 over k. And I know the 1 over k's are divergent, but they're bigger, so that means direct comparison doesn't help here. Right. So sometimes direct comparison is helpful if they fall on the right side of each other, but other times it doesn't. So I'm wondering, well, okay, so that doesn't help either, but let's see, these guys diverged, but I took half of them out. Maybe it'll converge. Okay. So I'm going to give you another theorem before I come back to playing more with direct comparisons, the limit comparison theorem. And this one doesn't relate to an inequality. We just have two different sums. We have these A's that are being added up, and we have these B's that are being added up. And we want both the A's and the B's to be positive terms. We don't want them to be negatives. And then what we do is we look at the ratio. What happens if I ignore the sums for just a moment and I look at the limit as k gets big of a to the k over b to the k? So I just match them up and I say, what happens when I look at their ratio? And what this does, it just compares their growth rates. Kind of like L'Hopital's rule does, but in a slightly different way. It's not exactly the same as that. If this has a limit, so it's some positive finite number, okay. And again, for the last several series tests we've been looking at only positive terms. We'll have to look again if the terms are negative or alternate in sign. That gets a little trickier. If there's a limit, then what that means is these both converge or diverge together. They grow the same way. Okay, so both series converge or perhaps diverge together. So usually the first thing I try after the divergence test is, can I do a direct comparison with a series I already know? Because direct comparison is pretty easy. It's just an inequality. And actually, a lot of times I find the limit even easier than the inequality, because some inequalities are tough to solve. We ran into a couple of those in the past. We got stuck trying to solve the inequality. We ran out of algebra tricks. So let's apply that to the series we have here. So I have my 1 over n's divided by my 1 over 2n minus 1s. And I want to look at the limit as n goes to infinity. Well, multiplying by the reciprocal of the denominator, this becomes the limit as n increases of 2n minus 1 over n. And I think, well, if these were x's, they would be polynomials. So they're still polynomials. And they both have the same degree, because this is n to the first power, and this is n to the first power. And we learned a while back that if we take the limit of a rational function, and the numerator and denominator have the same degree, then the limit is the ratio of the coefficients of those highest powers. So this must go to 2. Now you might ask, ooh, does it matter which one goes on top? Well, if I flipped which one was on top and bottom, then that means I just flipped the limit, and I still have a positive finite number when I flip it. Okay, so I'm good. This has a limit of 2, so that implies since the sum of the 1 over n's diverge, the sum of the reciprocals of the odd numbers must diverge also. And usually when we do something like this, we state clearly which theorem we use. So then I would say by the limit comparison test. All right, so we have 2 more tools on our belt. We have a direct comparison, which can show convergence or divergence. It's just a matter of saying, I wonder which sequence you're most like. And if we can identify that, we see what happens. So there are some cute problems in the homework. Let's grab one and test it out, see what we can do with it. Let's jump into 10.5. Oops, do it that way. All right, 10.5. All right, so, and some of the homework, they'll give you the comparative series, some of them they won't, it just kind of depends. So here, they want us to compare this crazy series up there with that one down there. So let me grab that as a screenshot. Come on, there you go. All right, so we're gonna compare these two here. All right, so why would the author of this problem choose to compare this? So this is the given one, and then this is the one we're going to compare with. So my train of thought on deciding what to do with this guy right here, first thing I do is I say, okay, forget about the sum for a minute. What happens as k goes to infinity with the individual things? Well, that's k cubed over k to the 8 minus 6. And from my work with polynomials, the denominator outruns the numerator, so it's going to infinity faster. If you're unsure of that reasoning, does anybody remember the trick for dealing with something like this here? What's that? Since it's infinity over infinity, you could apply L'Hopital's rule. Another trick before L'Hopital's rule you might have learned is divide everything by the highest power involved there. So if I divide everything here by k to the 8, then I'll get a new limit. I'll get the limit as k goes to infinity of, in the numerator, that's going to give me a 1 over k to the 5th when I divide by k to the 8th. Oops. Can't talk and chew gum at the same time today. K to the 5th. In the denominator, I'll get k to the 8th over k to the 8th, which is a 1, and then I'll get a minus 6 over k to the 8th. And then I say, okay, what are these guys doing? Well, as k goes to infinity, the numerator is going to 0. And the denominator is, well, that's 1. That part's going to 0. So this is going to 0 over 1. So I've just shown the limit is 0 with that trick. It's a little easier, I think, than L'Hopital's rule. L'Hopital's rule has us to apply derivatives. So again, always do the divergence first. If you can do it in your head, fine. But sometimes I need to write things down on paper. So the divergence test tells me nothing here. But it's always worth checking. So, oops, wrong here. There we go. So the other thing to consider is for big values of k, like a million, I'm a millionaire to the 8th power. Do I care about $6? No. So for big K, this thing essentially is, big K to the 3rd over big K, that's my big K, to the 8th, and big K to the 3rd over 8th is really 1 over big K to the 5th. Okay, so that's the kind of mindset as to why that one was picked for big numbers. So then I do, let's see, On one like this, I'm thinking solving an inequality where I throw in k plus 1s sounds like a nightmare. So let's see. Oh no, we don't need to do that here. Oh, that might work out all right. Let's just try a comparison test. So what do we know about this guy right here? Convergence or divergence? That is a convergent p-series because p is greater than 1. My p is 5. So that guy right there is a convergent p-series. P equals 5, which is definitely greater than 1, which is the requirement for a convergent p-series. So I'm hoping this converges too. So squeezing wise, if I want to use direct comparison, since this guy is convergent, I want those to be the bigger things being added up. And so I want those other things to be less than it if I'm going to use direct comparison. And so often I'll write this down or think, ooh, does this look reasonable or does this look like a pain in the butt to solve? Let's see, if I cross, everything's positive here, as long as k is bigger, ooh, usually want positive series. So I would want k to be bigger than what? I guess if I made k 2, that would be better. Cross multiplying, what do we have? Switch color, k to the 8th. Is that less than k to the 8th minus 6? Answer is no, it's not. So direct comparison fails here. So then I move on to limit comparison. And I don't know about you, it kind of depends on the individual. I find I'm better with limits of ratios than I am with inequalities. I find it's easier to make a mistake or get stuck on an inequality. So I tend to like the limit comparison theorem better than the direct comparison, unless it looks really easy. So the limit comparison says, all right, take the limit as k goes to infinity of one of these divided by the other. So I'm going to write the more complicated one in the top. So that's my main fraction bar, and then the 1 over k to the 5th goes in the bottom. So rewriting that, we're going to get k cubed. Let's see, the reciprocal of that is k to the 5th over 1, denominator, and then we have k to the 8th minus 6. Putting that all together, we have the limit as k grows forever of k to the 8th over k to the 8th minus 6. Two polynomials of the same degree. So what should the limit be? 1. And so by the limit comparison theorem, since the denominator series converges, the numerator series must converge also. Okay. So I state something like that at the end. All right, let us, what did they ask of us specifically here? All right, we want to use the basic comparison test. That's what I call direct comparison. And direct comparison didn't help us here. So let's see, the first series converges by comparison. The first series diverges by comparison. The basic comparison test is inconclusive here. What do you think? Yeah, the direct comparison was inconclusive. They were on the wrong side of each other. So I was like, oh, I don't know, it doesn't help. Okay. So then we move on to another kind of test, which was the limit one. Let's jump down here and see what we have. Use the comparison test, which is what the book calls it. Sometimes it's called basic comparison test, sometimes direct comparison. I tend to call it direct comparison. Pretty much everyone calls the other one the limit comparison test. What can we do with this guy right here? So let's take a peek. New page. Screen clipping, where'd you go? There you are. All right, so first thing I do is say, well, what if I just take the limit as these guys go to infinity, not even thinking about the sum yet, and I can see the degree of the bottom is higher than the top, so this goes to 0 term-wise, tells me nothing. That just means it's a candidate for convergence. It might not. So then I move on to something else, and I think, all right, well, for big N, this is like the sum as n goes from 1 to infinity of 1 over n squared, isn't it? Because for big numbers, who cares about a minus 6? Okay, so that's no big deal. So it's like that. So then I can say, all right, doesn't any, and I know this guy converges because it's a p-series with p greater than 1. So this is a convergent p-series. P equals 2, which is greater than 1. So if it's convergent, I want these guys to be bigger than those guys, and I wonder what that inequality might look like. And so I could say, oh, let's try direct comparison just for fun. For direct comparison, I'm hoping that the n cubed minus 6s over n to the 5th minus 6s, I'm hoping they are less than or equal to 1 over n squared. A little cross multiplication on that gives me n to the 5th minus 6n squared, multiplying up there, is less than or equal to, excuse me, n to the 5th minus 6. And since it's a slow Wednesday, I'm still not sure. The n to the 5th subtract out. And so I'm going to get a negative 6n squared is less than or equal to negative 6. Still having a hard time visualizing that in my head, so I divide by negative 6. Dividing by a negative, remember, we're going to change the direction of the inequality. So that would give me n squared is greater than or equal to 1. Well, if n is 1 or bigger, that's true, isn't it? So I say, yeah. Woohoo, it worked by direct comparison. That wasn't too bad. Okay. If you have any doubts about your algebra, what would you do next? A limit comparison, right on. Yeah, that's what we're going to do. So let's just do that too, just to see if we're on the right part. So I think by direct comparison, we have convergence here. By direct comparison. Limit comparison is where I'm going to take the limit as n gets big of one of these. So I'm going to take the n cubed minus 6 over, let's see, what was it, n to the 5th minus 6 divided by 1 over n squared. Multiplying by the reciprocal is going to put that n squared in the top here. And you'll see some similarities between direct comparison and limit comparison algebraically. So I'm going to distribute that into the numerator there. So what does that give me? That gives me n to the 5th minus 6n squared over n to the 5th minus 6. And I think, ooh, polynomials of the same degree. The coefficient of each highest power dominates. So that means this limit must be 1 over 1, which is 1. Since there is a positive finite limit, what do we know? They grow at the same rate, so if one converges, the other has to. So then, by the limit comparison test, we also see convergence. And you could just say the sum converges. I don't know why I'm writing it down again, because it's way too much fun to write all this down. Now, notice that some of these terms, let's see, I guess the first one is going to be negative. No, it's going to turn out to be positive. How about the second one? Oh, no, they're all positive. Okay, that works out. It's sometimes with the sequences, the first few terms might be negative. That's no big deal. But if infinitely many of them are negative, then we have to rethink our strategy, especially if they alternate sign in any way. Then it gets really tricky to figure out what's going on. All right, well, I think that's good for today. So I'm going to stop here if I can figure out how. Stop.